welcome to my project video. My name is Nadeem and my project partner is Bell. In this video, we'll be showcasing the airfoil geometry prediction tool we developed using neural networks in MATLAB. The main goal of our project was to create a machine learning model that can predict the shape of an airfoil based on its aerodynamic performance. We trained the model on a large data set of airfoil geometries and performance values, and we also built a custom GUI, which is the graphical user interface, to make it easier for use. In this video, we'll walk you through how the model works, demonstrate how the uh, graphical user interface works, and show how the predictions can be exported for further use. So if you're interested in this aerodynamics, neural networks, or just want to see a cool engineering project in action, stick around. So before we start our project, we had to collect our data. So we collected our data from this repository. I'll provide the description. The, I'll provide the link in the description. So our airfoils are Eppler series. So if you scroll down, you can see the Eppler series. It's here. So all of this is for the Eppler series, all the airfoils. This is the DAT files. We downloaded the DAT files in batch. Yeah, downloaded all the DAT files exported in this folder. So right now, all the airfoils from A to Z, all of them are here. We exported the ones we need, which is the Eppler series. All the letters, all the airfoils which has E in it is basically the Eppler series airfoils. So we used these DAT files to export some other informations, the performance of each airfoils. We used XFLR 5 software. We actually exported the DAT files here. You can see so here's all the airfoil DAT files that we need for our project. So if I just load this, yeah, all the airfoils are now uploaded on this software. So after doing some simulations, we were able to export the performance extra datas in our Excel format files, which is some sort of like so these are the all performance data with its DAT files for each airfoil. So the total is 200 2304 files altogether. So let's see. This is how the data points for each airfoil look like. We simulated for angles between -25 to +25 at an increment of 0.25, and we got different parameters here for 11 different Reynolds numbers. The Reynolds numbers we specified is 50,000, 100,000, all the way up to 1 million. And we did this for all the airfoils. So this is the collection of our data. Yeah. So how we collected the data and exported into MATLAB. We wrote a code for this to export the data into MATLAB. So let me just run it. So here you'll see all the progress, all the airfoils that has been exported. We are actually trying to create a data struct in MATLAB so that we have organized information of how our data set looks like. Right now it's still exporting. So now the data is imported into MATLAB, and the data struct is created. So if we look into it, this is how it looks like. All the airfoils. There's a main data set, which is the performance data, and its corresponding geometries. So for one airfoil, there's around 11 uh, separate files containing the data. So this is the raw data from the Excel file and the DAT files. So if you see one of the files, this is just exporting the way it is in the Excel file. This is for the performance data. And if you go back and see the geometry, this is the coordinate file to plot the airfoil geometry. So the first column is X and the second column is Y. Go back. So what I've done is I've saved the workspace for this MLX file. So the reason I saved this MLX workspace is to use in a separate script so that I can do further data processing. This is to just avoid running this script again and again to export all the data and do all the data struct and all that stuff again, like repeating all that. So I've saved this in a .NET file, the workspace. It's in the program files folder. Uh, if like there's a met file named workspace raw data. So this is actually loaded. We have two files. One is the MLX file raw data extraction, which did the data struct, created the data struct, and the second file is the main file. This loads the workspace from this MLX file, the previous one, and does the processing of all the data in that struct. So as you can see, it calls the met file that I said that we saved. It does all the data cleaning, EDA, and IDA it does the correlation plot. And in feature engineering, let me just run this to show. Let's clear this one. So if I run this, it will again load the workspace. So yeah, all the workspace files and variables just came. So when when I run this section, it actually removes the rows and columns that are not important for us. So right now, if I open this struct, this is the place where I have like the main information about the struct. So this is the main performance data from the Excel file. So right now there's a lot of rows that has missing values and which are unnecessary, like the headers. We only need the information from row 6 below, and as you can see there's unnecessary data which has all the zeros in it, so we can remove that. So if I go back, we run this. So now the table looks like this. What I've done is remove the unnecessary columns, and the headers I have labeled it in a table. So all the data points are in this table. After doing the data cleaning, we do the EDA to see the correlations between each plot, each variables. So this is the correlation plot that I was talking about. So this plot actually ranks each variables against each other to see which values, which variables have more importance or less importance to each other. So this is what this code, EDA code, does for this project. And for feature engineering, we did add an extra variable, which is the ratio, the lift to drag ratio, and we did PCA to remove unnecessary variables, which is the column values features that won't be used to train our model. And we also did the graphical user interface to visualize all the plots in under one figure. So I can run this. So this is the graphical user interface that I was talking about. So here there's a drop-down menu to select which Reynolds number and airfoils you want to choose. So let's say I just randomly pick one, and in this drop-down menu, the plot type you want to select. So let's plot this one. So here's the plot. If I change the plot, let's say the geometry, I want to see how the airfoil looks like. Just click plot. and see the geometry. So let's say I want to see a different geometry. I click select a different one, click plot. I get a different geometry. So this GUI is basically for the existing data. It's not for the trained model. So actually we have two GUI, which is this one and the another one that like gives the predicted values and shows it in a plot. So in feature engineering, adding the CL over CD. So if I open the struct again, you'll notice that we've added another column here, the ninth column, that's the CL/CD. This is the ratio of CL and CD. So in this section, we do coordinate geometry flattening. Basically what this means is we flatten the geometry. Let's say in these coordinate geometry files, the DAT files, um, the coordinates are in like row by column, which is in two columns, and let's say I think 62 columns. So what flattening does is we have all the data points in one row, and it becomes a one row and 62 columns. So if I run that code, let's see what happens. So this is the coordinate geometry. We haven't done anything in this file. We use this data to actually populate the performance data. So here, as you can see, the performance data finishes in column 9, and from there, all the coordinate plots, the data points, goes from there. So all this like X and Y, all all the data points are in one row, and it is repeated for all the alphas, all the rows, until we have a change in geometry, which is after changing after the 11th Reynolds number files. So as you can see in the data struct, we have 11 here. So this 11 files is for one airfoil. So after this 11 um, files, the next loop starts. So this is how we'll train our model. First 9 columns will be for the features, input features, and the other 10 beyond, it will be our output, which is the coordinate geometry. So if we like input, give an input which is not in this data set, let's say a new input in the performance. So what the model will do, it will learn these data points, and it will try to generate a new set of airfoil which will match the performance that the user is trying to get for. So after doing the flattening of the geometry coordinates, we go for resampling of this coordinate geometry. Since it's a large number, we try to get a target of 50 points only. Uh, Initially, it's around, I think, 100 to 200 points. So, the reason why we are reducing the target data points for the output is because uh, the model has a time constraint. It will take a lot of time if we have a lot of outputs. So we have to uh, do it in a shorter time. So if we run this code for resampling, and the other reason why we are doing the resampling is because like in the data struct, not all the files have the same table size. So just because like the coordinate geometry, some have different file size. The row by column is different for some certain airfoils. So after resampling all the data points, we combine everything into one big table, which will be used to train the model. So after we combine all our data points in one table, so this table is stored in a variable called training data table. It's here. So right now the table contains 367,768 rows and 111 columns. So in order to decide which input variables are we going to use for training the model with PCA, find which input variables are the most important ones. So we got the first four ones, and we did some more EDA. The biplot and the 3D biplot is here, and we extracted the predictors and response in separate variables so that it's easier for training, and we saved that in a mat file as well. It's called nn training data.mat. It is saved in the program files, so it can be used. We used it in neural fitting tool to load the data and train the model. So if you go to the tools section, this is the tool we used to train the model. So here we did the importing of the data, tagged the predictor variables and the response variables, and we trained the model for after data splitting and all that. Then we saved it in a separate folder. It's called Model 1 Levenberg algorithm. Here we have a function file, two function files, and one mat file. So what these files do, actually, there's a script as well, .mat script. This is basically if we want to rerun the model again to train with the new data and define the data splitting here. and the neurons, how many neurons we want, and this is the function file. After the model has run, it saves automatically. So if we want to use the predictor tool, so all you need to do is you can call this function file predict airfoil GUI. So predict, this is the name of the airfoil, the tool. So this is how the graphical user interface looks like. This is the input variables that it asks. So let's say we input the angle is -23. Let's give random numbers. If we click plot geometry, it is supposed to plot something. Yeah, let's say we change the number. Say I change 20 to 20, 23 to 26, then plot again. It is supposed to give different points. So here you can see the differences. Maybe you can have some other variables changed. 0.639, let's say, of the geometry, so that plots change. And if we want to export, we can also export the data points in a Excel file. So that's basically how our predictor tool works. So if we have different data points, if you want to load with different data set, you can also do that. Just have to save in a file this .mat file and in training data.mat. I have also uploaded this project on my GitHub. I will also provide the link in the description below. So all the files, like all the data files that I have used to create the model, and the program files, just basically what I've showed in the video. It's all here, and also a README file. There's a blog here to that explains what each code does and what's the result it's supposed to do. All of it is like available on GitHub. Hope you enjoyed the video. Thanks.